Okay, right. Hello everyone. Welcome to the laboratory for a little experiment. This one is about the absorbance spectra of leaf pigments. It follows on from the practical we did on photo and chromatography recently, where you saw that plants, although they look just green, have in fact got a variety of pigments in them, all concerned with photosynthesis, but different colours, and you remember them separating out up the chromatography paper. Not only are there lots of different pigments in plants, but the pigments that plants have actually absorb different wavelengths of light energy, which is very important for plants because it means they can harvest energy across a bigger spectrum than just having a single pigment. So this is to look at which wavelengths of light are absorbed most of all by plants and which the least. Okay, so I'll take you through this a stage at a time. First of all, you need to have a bit of plant. So here's a piece I found earlier, lovely lush light green plant. Obviously got lots of pigment in there. So the first thing I'm going to do is to remove some of the leaves from the plant and put them in the beaker here. I apologise to the plants obviously before I did this. Okay, so there we go, there's a few leaves in there, marvellous. Now I'm going to cover them with boiling water. So I've pre-boiled the water here, I'm putting that on there. So what I'm basically doing is cooking the leaves, aren't I? Exactly what you'd do if you were making your dinner, if you were cooking some vegetables. You'd put them in there. This will really help, does it? I'll pop that over there. There we go. You put your green veg in the water and you boil it up for a bit. So I'm just going to give it a good stir around. I do this for just a few minutes, not long at all, 3 or 4 minutes is usually enough. The idea being that I'm softening up and killing, but softening up the vegetable material, the plant material. I'll move these ones out of the way. If I had lots of time, I'd like to do some of those as well. I mean, that's tremendously big and green, isn't it, that one? See what we got out of that. Now, these are already getting nice and soft. The stems don't really get soft, of course, because the stems are primarily sort of supportive tissue and are carrying water and mineral salts and things around the plant. So we've got xylem and phloem in them, which is quite robust. So they tend not to go soft particularly quick. This is starting to look about ready. Okay. Just give it a minute or two more. Squeeze, squeeze, squeeze. That should be about right. Now, that hasn't extracted much in the way of anything, has it? It's still just green plant in water. So I need to put the plant leaves in a solvent which is going to be able to extract that pigment from my leaves. And that solvent is called ethanol. And here I have Here I have a boiling tube, and I'm going to put some ethanol in the bottom, about that much. That was quite a generous amount of ethanol, actually, a bit carried away there. Pop the lid back on. So there's ethanol in there. Now that ethanol's cold. It would actually be better to have it warm. So what I'll do is I'll pop that in there, and I'll get the leaves out and stick them in the ethanol. The reason I'm doing it this way round is because ethanol has a much lower boiling point than water. So if I stand it in boiling water, if I stand the boiling tube in boiling water, then the ethanol itself will actually start to boil, I hope. Pop these leaves in. Come on. A bit reluctant to go in these. Right, that should be enough leaves, I think. I'll take the others out of the water so they're not a distraction to us. There we go. And now I'm I'm just going to feel the temperature of that with my hand. Ouch, that's very hot. So that's more than hot enough for the ethanol to boil. So I'm going to help it a little bit by stirring it with the spatula. Just to make it sort of get right into that tissue. And I can see lots of bubbles coming off there actually. You can see it boiling. You have to leave it in there probably about 5 minutes so that the ethanol can extract the pigment from the leaves. He says, hopefully. Starting to green up a bit. You can probably see that the liquid above the plant is actually starting to go green. It's quite a thick sort of cuticle on this plant, so that's why I'm being quite vigorous about squashing it up a little bit in the ethanol. Because if it was something like lettuce or parsley, which is really quite a lightweight sort of plant, then the green would come out more readily, but it's okay, it's fine, it'll work. Just checking the temperature again. Still warm, but it's not quite hot enough yet, so I'm just going to put a little bit more hot water in there, just to keep it warm. And I'm going to stop it there, because I think it's green enough for what we need to do. Now, when I did this as a practical with the class, we looked at 4 different types of plant, but I'm just going to look at the one today, just this plant, just to show you the technique, because that's what's important. So now I've got my extract in here, nice and green, lovely. So I'll just pop that into there. Now, to find out which wavelengths are absorbed the most by the pigment, I need to use a machine like this. This is called a colorimeter. Basically, it has a light source here where I'm pointing, and that light source inside the box shines in that direction onto a light detector underneath here. On the way through, it passes through a filter which only lets light through of a specific wavelength. And if I look down into the machine, I can see a number. This one says 440 nanometers. That's the wavelength of the light that is passing through, it's allowing to pass through. There's a ring on the side, which if I push the ring, it will click along to the next wavelength. That one is 420. No, it can't be. 440. 440. 470. Thank God. 490. 520, and so on. The exact wavelengths we don't want to worry about just at the moment. Now, each of these wavelengths actually represents a different colour in the visible spectrum. We all know about the electromagnetic spectrum, and there's a little bit in the middle which is visible light: red, orange, yellow, green, blue, indigo, violet. That is the visible spectrum. We humans work using the visible spectrum, most animals do too, and believe it or not, so do plants. So plants are absorbed differently at those different wavelengths of light. So now this bit's quite important to watch what I'm doing here, because I've got a little square test tube which we call a cuvette here, which has got ethanol in it. So it's a cuvette plus ethanol, and I'm going to put that into the space in the colorimeter and press reference, which is marked here with a big capital R. That is to zero the machine to ignore basically any light absorption caused by the cuvette and the ethanol. So I'll press that and it's gone to 0. I can now take that out and get another cuvette here. Pop that one in there for safe, because they're made of glass, so they're quite fragile, these. And this cuvette here, exactly the same as the one I've just used, except that one's got ethanol in. This one I'm going to put my pigment into. So I take some pigment out of here, and I'm going to put pigment into my cuvette. And that's worked really well, hasn't it? It's a nice looking green colour there, very chlorophyll-y, isn't it, that one? Nice and green. I'm going to put that into here, and I'm going to press the T for test. Okay. And it's going to give me an answer of 1.75. That's quite a good number. I've got a pen with me to write on the board. Yes, I have. Excuse me. Just go off screen a second. 1.75, brilliant. Now I continue to work on this, get that out of the way, I don't need that anymore. I've got my colorimeter here, so I'm now going to re-zero it, so re-reference. Actually I need to check it onto the next one, so this is 470, reference it on 470, so that re-zeros it. And then put my cuvette back in and test it. And it says 1.49. 470, 440 nanometers. Very small nanometers. Take it out, turn it on to the next wavelength, which is 490, zero it, put the pigment in, press test, 0.91, 0.91 absorbance, 490. Take it out. Reference it. Pigment in, test. 0.81. Did I move it on there? Not sure I did. Better check that one, because I might not have moved it on to the next one. 490, I didn't, you know. Right. I really can't see. 520 this one is, so this is 520, so I'm going to reference it at 520. There we go. Put the pigment in, test. 0.65. 0.65. 520 that was. Exciting, isn't it? Zero it again, but move it on. 550 this one, here we go. 0, put that in, test. 0.53. 550. 550. 0.53. Take it out. Put the reference in, move it on. This one is 580. 580. Now you probably see a trend there, can't you? I wonder. 0.4. 580. 0.4. Brilliant. Reference, move it on. 590. 0.37, it's still going down. 0.37. 590. 680, that's a big jump. There we go. 0.53. 680. That's the highest one on this one. I thought it went up to 700, but apparently not. Not this one. This one just goes to 680. Okay? Right, so that's basically the experiment, and I've put that data on the board here. I just want to look briefly at the data. You can see these figures are absorbance. That means how much of the light is absorbed by the pigment. Okay? So it's not how much gets through, it's how much is absorbed. So this is a sort of number representing the efficiency of that pigment in absorbing that wavelength of light. The maximum number we can get to in absorption on here is 2.0. So 1.75 is well up there, and that means that that particular wavelength is actually being absorbed a great deal. And as we work our way down through these, or up as it happens in numerical manner, through the nanometers, through the wavelengths, we see that less of the light is absorbed by some of these colours, okay? Until we get to the bottom when something strange happens, it starts to go up. And if I had got a 700 one as well, it would probably be higher than 0.53. Now, the interpretation of this is down to exactly what colour those wavelengths are, because this end up here, 440, is red. Now red and infrared are fairly long wavelength radiations, okay? Long wavelength radiations go right down to things like radio waves, are not as energetic as the blue end of the spectrum. And this down here is the blue end of the spectrum, and that's much more energetic, the wavelengths there. If we went on down from here, blue, we'd go to ultraviolet, and you'd start ending up with places like gamma rays and X-rays, which are very high energy radiation. So, remember what I said, red, orange, yellow, green, blue, indigo, violet. So we're going down through the colours, and it's about here, this region, but let's put the red on it, that's another colour I've used elsewhere. This region is yellowy blue, sorry, yellowy green, yellowy and green. So red, orange, yellow, green, blue, indigo, violet out of our range because of the machine can't detect at those levels. So the higher ones up here are this red end of the spectrum. The higher ones down here, or the higher one, because we haven't got any more data down there, is the blue end of the spectrum. And the lowest figures on the board are in this region here, okay, 0.4, 0.5, 0.6, and that's the middle of the visible spectrum, around about the yellowies and the greens. And what that's saying to us is that plants do not absorb as much in the green and yellow spectrum as they do in the red and blue, which is absolutely true. That's absolutely correct. That's why plants look green. The reason this plant looks green isn't anything fundamentally green about it, it's because the light is being reflected from it, because green light's not much use to plants. If I was to shine red light and blue light on this, it would be absorbed into it and the plant wouldn't look green. It's a funny experiment, that. if you shine red and blue light at the right wavelengths onto a plant, the plant actually looks black because it absorbs the red and blue radiation. Okay, so there we are, the absorption spectrum of leaf pigments. I hope that was some help, even though, yeah, it was a bit funny in places, wasn't it? But we didn't get any more data lower down, but not to worry. Okay, bye for now then. Oh.